Hi guys, welcome to the new section, Convolutional and Recurrent Neural Networks. We start with the first video, Optimization Techniques for CNNs. Let's apply pooling layers. A popular optimization technique for CNNs is pooling layers. A pooling layer is a method to reduce the number of trainable parameters in a smart way. Two of the most commonly used pooling layers are average pooling and maximum pooling. In the first, for a specified block size, the inputs are averaged and extracted. For the latter, the maximum value within a block is extracted. These pooling layers provide a translational invariance. In other words, the exact location of a feature is less relevant. Also, by reducing the number of trainable parameters, we limit the complexity of the network, which should prevent overfitting. Another benefit is that it will reduce the training and inference time significantly. Now, we will add max pooling layers to the CNN, and at the same time, we will increase the number of filters in the convolutional layers. First, we will import all necessary libraries. Next, we will load the MNIST dataset. After that, we will reshape the training data to represent grayscaled image input. We will normalize the input data. One-hot encode the labels. We will define the CNN architecture and output the network architecture. Further, we will define the callback function and set the network hyperparameters. Finally, we will train the model. The training process may consume some of your time, so meanwhile, go and grab a cup of tea. Let's show the results on the test set. By applying a max pooling layer after each convolutional layer, we were able to decrease our error rate. Now, we perform optimizing with batch normalization. Another well-known optimization technique for CNNs is batch normalization. This technique normalizes the inputs of the current batch before feeding it to the next layer. Therefore, the mean activation for each batch is around 0. And the standard deviation around 1, and we can avoid internal covariant shift. By doing this, the input distribution of the data per batch has less effect on the network, and as a consequence, the model is able to generalize better and train faster. Now, let's show you how to apply batch normalization to an image dataset with 10 classes. First, we train the network architecture without batch normalization to demonstrate the difference in performance. Using these lines of code, we will import all necessary libraries. Next, we will load the CIFAR-10 dataset. After that, we will normalize the input data. One-hot encode the labels. We will then define the CNN architecture and output the network architecture. Now, let's define a callback to prevent overfitting. We will next set the network hyperparameters. Finally, we will train our first model. The training process may consume some of your time. Now, let's add batch normalization to our network architecture. Now, we're ready to train the model that includes batch normalization as well. As you can see, the training is completed. Let's plot the validation accuracy of both models to compare the performance. The results of both models are like this. As you can see, the model with batch normalization takes the lead on validation accuracy after a couple of epochs and manages to stay ahead of the model without batch normalization. With a maximum validation accuracy of 84.16%, compared to a validation accuracy of 83.19% for the model without batch normalization. Now we will print the validation accuracy with batch normalization and without batch normalization. As you can see, the validation accuracy with batch normalization is 85.64%, and accuracy without batch normalization is around 83%. The model with batch normalization also converges faster. However, with 25 seconds per epoch, the model with batch normalization is slightly slower per epoch than the model without batch normalization.